So what the main purpose of this lecture is to show you how to transform from the differential equations that you wrote down at the beginning of this lecture that summarise what we've got to so far. Those differential equations you need to transform back to the integral forms, because they will then explicitly show you how to solve for the continuity of the fields across the boundary. So if I just I'll redo that drawing specifically now for the electric field case. So we'll start with the fields. The electric displacement vector. We had that the divergence of the displacement vector was equal to 4 pi rho. So how do we get back to the integral form from that differential form? It's a classic exam question from past years. No one's got any idea. If you go back a few weeks, you'll see that both these terms existed under a common integral. It was a volume integral.
Closed integral.
So if you had your volume element, we can take here rho, it had a volume element. And we're integrating over a volume here, and we integrate over a volume there. Using Gauss's divergence theorem, or some people just say the divergence theorem alone, what we want to do is to convert the left-hand side to a surface integral. So you know the general form of the divergence theorem. So you want to go from the volume integral, so there's your element of integration, some unit volume, and the argument is an adder operating on the electric displacement vector. It goes to a surface integral, and it consists of a surface element of integration, delta sigma, and it projects the displacement vector onto the unit normal of the surface. Yes, you recognise that as Gauss's divergence theorem. You've got the transformation from the volume integral to the surface integral. The argument under the volume is the divergence of the vector field, but under the surface integral we've got the projection of the vector into where the surface normal's facing. Now, as with everything I've done so far with you in this course, the idea is to understand this thing in terms of an actual picture, to convert it to the experimental case. And we note here that to complete the equality, we've got our volume integral, element of integration is the unit volume, and then you've got the charge, the volume charge density. And so, you literally draw a picture that describes what's being said by that equation, that integral equation. So you see here that we've transformed originally from the differential form of Coulomb's law, which was that 4 pi rho, directly through via the divergence theorem to the original integral formulation that we had at the very beginning.